So this is a talk which I gave at the recent BMLA conference in Liverpool in May 2024, and this talk concerns the modelling of the heat conduction losses during long pulse widths in laser and IPL treatments, particularly in hair. I have no potential or actual conflict of interest in this regard. So I constructed a one-dimensional heat conduction model to look at what happens when we heat up the melanin in a hair shaft. So it's pretty much like this. We fire the light energy at the hair shaft at one diameter, and in there, that tiny wee red stripe in the middle there, that's where all the heat is generated from the hair, from the absorption of the light rather, and it then conducts outwards into the surrounding tissue. The model setup is like this. I used a spatial grid with 10 micron boxes that extends out to 3.76 millimeters in distance. On the left hand side we have the melanin in the hair shaft, and I can change the radius of that to whatever I desire. The original temperatures are all set to 35 degrees Celsius at the starting point, and then we look at the temporal evolution of the hair of the temperature distribution. The time steps are 0.1 milliseconds, and this extends to 3.2 seconds in total. So the idea is that the melanin is heated up by the light energy. That then generates a temperature profile which we can then watch as it evolves over time. And this is a snapshot from one of those runs with an alexandrite laser at 755 nanometers, fluence of 10 joules per square centimeter in a 10 millisecond pulse. And this is the hair shaft wall, the follicle wall where the germ cells live. The dermis at there, and the pulse width ends at this point here. And you can see that the red colour is the red colours indicate where it gets quite hot. Yellow and orange are a little bit cooler, and green is the background dermal temperature. So we have fluence surrounding this hair, and in particular this hair diameter. The fluence at that point is 10 joules per square centimetre. It doesn't matter what the depth is, we can account for depth in a later calculation. And assuming a Beer-Lambert absorption profile with no scattering as a first approximation, then the fluence distribution inside a 60 micron hair looks like this. So at the surface we have 10 joules per square centimetre where the fluence meets the melanin. But at the other side of the hair, when the light is progressed through the hair at 60 microns, the fluence has dropped to just slightly under 4 joules per square centimetre, and then the rest of it is lost to the surrounding tissue. And then from the other side, because of course it's a one-dimensional model, so we get hair coming from both sides, then we've got fluence coming from that side too, and it's basically the I suppose you could say the flipped opposite of the first fluence. It's just almost exactly the same but in the other direction. And what this means then is that the total fluence in the hair, this is a 60 micron hair, so quite a thin hair, total fluence at the surface is just under 14 joules per square centimetre, and at the centre of the hair it's just slightly more than about 12 joules per square centimetre. And that's because fluence is additive. It's coming from both directions in this model. In the 3D world, it's coming from all directions, but we can add them up like this to find what the total fluence distribution is in the hair. And then in a 200 micron hair, which is a very thick hair, the fluence distribution looks more like this. Because more of the light energy is absorbed within the hair, less reaches the other wall, the other side as it were. So the accumulation at the walls is lower than with a 60 micron hair. So the total here is only slightly more than 10 joules per square centimetre, whereas in the centre it's just slightly less than 4 compared to just over 12 with the 60 micron hair. So that the hair thickness has a significant influence on the distribution of light inside the actual hair itself. And this will of course have an effect on the temperature rise. So if you look at 4 wavelengths here, we've got the Nd:YAG 1064 wavelength, we've got IPL at 824 nanometers, which is an averaged wavelength, diode at 810, and then the alexandrite at 755. And these curves show you where or how the fluence distribution operates inside a 60 micron diameter hair. Now, this is important because this gives us an idea as to the temperature rise that's going to be created by that fluence. But the temperature rise depends on not only the fluence distribution inside the hair shaft itself, but also the corresponding absorption coefficient. So we can use this little equation to calculate these temperature rises, where mu is the absorption coefficient, H is the fluence, joules per square centimetre, and rho C is the volumetric heat capacity. Now, interestingly about this equation, if you combine the top two elements here, mu H, you find that this is the energy density in joules per cubic centimetre. A lot of people call the fluence the energy density when it's not. You have to combine it with the absorption coefficient to find the real energy density. Fluence is fluence, not energy density. Rho C in the bottom here, the volumetric heat capacity, this can be viewed as the energy density per degree Celsius. So that when you combine these two, the numerator denominator here, we find the temperature rise. But, and it is a big but, I cannot lie, this is an instantaneous temperature rise only. It does not consider the loss of heat energy during the pulse itself. And that's what we're going to have a look at now. But before we do that, let's compare the temperature profiles across a hair diameter for the 4 different devices we mentioned earlier. So the solid blue line here shows the temperature profile at the end of a 10 millisecond pulse from an alexandrite laser. This is in a 200 micron diameter hair, so it's a big, thick, juicy hair, and with an incident fluence of 10 joules per square centimetre. And again, we're assuming a Beer-Lambert absorption profile with no scattering. So the solid line is the temperature profile at the end of a 10 millisecond pulse. The dotted line shows this temperature profile having relaxed, and this is the point where the temperature at the follicle wall has reached a maximum. So the follicle wall here looks like the maximum is about 42 degrees or so, something like that. And that temperature will not increase over time. This is the maximum temperature that it can reach. For a diode laser at 810 nanometers, well, the solid line shows the temperature profile inside the hair shaft itself, slightly lower than the alexandrite because it's got a lower absorption coefficient, and the dotted line shows the profile once it's relaxed, reaching a maximum temperature at the follicle wall. And then for the IPL, this is the averaged output over the range 600 to 1200 nanometers, which is typically used for hair removal. Again, the green line solid line shows the temperature profile at the end of the pulse, and the dotted line when the follicle wall is at a maximum. And then finally, the yellow curve here, the solid line shows the YAG 1064. It's not nearly as high as the other three because the absorption coefficient at 1064 is quite low compared to the other 3 wavelengths. And then also the dotted line, the yellow dotted line shows once it's relaxed a bit. So what is the effect of pulse widths? Well, during a long pulse width, the heat can escape from the hair into the surrounding tissue. And so as a consequence of that, the peak temperatures in the hair, the melanin, the hair shaft itself where the melanin is, the peak temperatures going to be lower compared to an instantaneous temperature rise. But what happens to the temperatures at the follicle walls where the germ cells live? And the germ cells appear to be the real targets in hair removal treatments. Well, this shows the temperature profile at the end of a 1 millisecond pulse for an alexandrite laser, again with a 10 joules per square centimeter incident fluence on the hair, on the melanin rather. And this is in a 180 micron hair diameter. I don't know why I changed from 200 to 180, I just did. So at the end of 1 milliseconds, it looks like this. At the end, at 282 milliseconds, this profile will have relaxed into the lower profile there, where this is when the germ cells or the follicle wall has reached the maximum temperature. And this temperature is, again, you can see is about 42 degrees, something like that, for a 1 millisecond pulse. For a 10 millisecond pulse, the red line shows the profile at the end of 10 milliseconds, and at 287 milliseconds, when that profile has relaxed, then you can see the red line at the follicle wall. Then for a 100 millisecond pulse, we see the green curve here, and at the end of 338 milliseconds, it has also relaxed. Now, the interesting thing here is that you've got the three profiles in the hair shaft itself, with the melanin which has absorbed the light, and they're quite markedly different. But the temperatures at the follicle walls where the germ cells reside are almost identical for all three pulse widths. So it seems that for the same fluence but three different pulse widths, the temperature time history at the follicle wall is virtually identical. So how do we increase the temperature at the follicle wall? Well, if we fire in a 30 joule per square centimeter pulse fluence rather, then you see the blue dotted line there. This is for a 1 millisecond pulse at 30 joules, and when that relaxes, it will form this line here, and you can see that the temperature at the follicle walls has increased significantly. It's now 54 something like degrees. So changing the pulse width doesn't appear to change the temperature time history of the follicle wall significantly, whereas changing the fluence has a major effect, much more influential on the temperatures there. So it appears that the fluence and the pulse width only determine the peak temperatures and the temperature profiles in the hair shaft, where the melanin is actually absorbing the light energy. But the pulse width has no significant influence on the temperature time histories in the follicle walls where the germ cells reside. Basically, it is the total energy absorbed which determines the final temperature profiles across the follicles, not the pulse widths, the total temperature. So thank you for listening, and I will keep on working on this kind of material, and hopefully get some new stuff out quite soon. Thank you.